So in this lesson, we are going to go ahead and prove Euler's theorem. So this is the generalization of Fermat's little theorem, which we conjectured by following in the footsteps of Euler in the last lesson. As a reminder, Euler proved Fermat's little theorem in 1736, but it would take him 27 years to do the work that we are going to be doing in just one lesson today. But of course, we have the benefit of hindsight and being able to take the shortest path from A to B, whereas Euler spent a considerable amount of time trying to develop the machinery, which we will go over today. But before we continue, I want to mention a couple of things regarding Euler, since he's going to be a pivotal figure in this course, and an event that happened 2 years after he proved Fermat's little theorem. So in 1738, Euler would lose his eyesight in his right eye, and Frederick the Great of Prussia, under whom he was employed, came to refer to him as Cyclops, which to Euler retorted, "Now I have fewer distractions." Euler, over the course of his lifetime, settled many of Fermat's claims, but also uncovered areas of mathematics that would later be developed into a much bigger field. And I want to go ahead and start off with one example of one of Euler's deductions, which is in the realm of analytic number theory. So let's go ahead and start off with this infinite product from n equals 1 to infinity, and we have 1 minus q to the n. So this here is just going to be the product of 1 minus q times 1 minus q to the second power, 1 minus q cubed, 1 minus q to the fourth, and so on and so forth. So this is an infinite product. Let's not worry about convergence of this. Actually, in Euler's time, the notion of convergence, as we covered in calculus, was not even a thing. That was discovered in 1768 by D'Alembert. And so when Euler considered these sort of infinite products or infinite series, he didn't care about whether they converged or not, but he was just rather more interested in expanding them and how what patterns arose from them. So if we look at this, we can see that the product is going to be 1, if we just multiply all the 1s over to themselves. If we want to get q, only 1 power of q, then we can take this q, multiply it to this 1, and then just continue multiplying to all the ones that follow. And so that will give us a minus q. If we want to get q squared, then we can take 1 times minus q squared, and then multiply minus q squared to 1, and then just so on and so forth. So we have 1 minus q squared. If we want to get q cubed, well, we can do the following. We can take q, negative q, times negative q squared is going to give us a positive q cubed. So that will give us one possibility, and then multiply everything else by 1. So we have a 1 here. But if we go ahead and observe that if we then take this q cubed over here, so we have 1 times negative q cubed times 1, then we have a negative q cubed, so it's going to give us a negative 1, so that's going to be a 0. For q to the fourth, we will see that to get q to the fourth power, we need to multiply this negative q times this negative q cubed, which will give us a positive q to the fourth. So we're going to count that as a 1. But then we also have this negative q to the fourth over here. And so we can do 1 times 1 times 1 times negative q to the fourth, and we have a minus 1 there. And so we'll have this. Last one. So now we can go ahead for q to the fifth, do q squared, negative, and then negative here. We're going to have a positive q to the fifth, so we're going to go ahead and put that as a 1. How else can we get q to the fifth? We can go ahead and take we can get minus q, and then multiply it to minus q to the fourth, and then we have a q to the fifth. And so that'll be a 1 there. But now if we look over here, there's a 1 minus q to the fifth over here that we didn't write down. So that'll be 1 times q to the fifth, and then we're going to have a minus 1 for that coefficient. And so if we continue in this fashion, we're going to get that the next non-zero term will be q to the 7 minus q to the 12 minus q to the 15, so on and so forth. And so what we have is that this expansion seems to look like, at least from what we have computed, it has the following form. So the story goes that Euler computed the first 20 of these terms by hand and was able to deduce a pattern. Other stories say that he computed the first 50. But what is known is that in 1740, Euler conjectured, had he been Fermat, he would have just said, this is true, I have a proof, which the margin is too small to contain, but he was not Fermat, thankfully, and he just took it as a conjecture. We have 1 minus q to the n, and he said that this is equal to the infinite sum, where now the n values are going to just be any integer. And then we have negative 1 to the n, and then we have that this is raised to the n, to the to the n, then 3n minus 1 over 2. Now, a number, so we say, so definition, that an integer k is a pentagonal number if k can be written in the form n times 3n minus 1 over 2 for n in the integers. For some n for some integer n. The reason for the name pentagonal is due to the following. So the reason for the name pentagonal numbers is because if we start with n equals to 1 and plug it in here, we just get 1 point, and then that's just going to be 1 point here. But when we plug in n equals to 2, we get 5. And so we're going to go ahead and draw this pentagon. If we plug in n equals to 3, we get back 12, which corresponds to the number of points if we go ahead and increase the array of points for our pentagon here, and then nest it inside our larger pentagon. And so that there will be 12 points in here. Similarly, if we do n equals to 4, now we have more nested pentagons inside in this array structure, and that will correspond to 22 points. Plug in n equals to 5, we get 35, and we have this array here. And so Euler realized that this expansion that we were just looking at seems to have the equality with this infinite sum. So this is a major branch of what is now known as modular forms, which takes place inside the realm of analytic number theory. So Euler conjectured in 1740, and often when Euler was unaware of how to go about doing a proof, he would correspond with mathematicians and ask them for their advice and counsel if they had any ideas for how to proceed. And so the following is one of my favorite quotes in mathematics. And so the story starts with a letter that Euler wrote to Daniel Bernoulli shortly after discovering this conjecture that we had, that this product should be equal to the sum. And so Euler essentially said something to the effect, "Hey Daniel, any idea for how to prove this?" To which Bernoulli responded with the following quote: "This can be shown in a most pleasant investigation, together with tranquil pastime and the endurance of pertinacious labor, all three of which I lack." And one thing that is definitely true of Euler is that he was not lacking in these three. He eventually did prove this, even though it would take him 10 years. But it's nothing compared to the struggle of what we are going to be covering today, which is Euler's theorem, which he proved 27 years after having proven Fermat's little theorem. So 3 years after Euler proved the generalization of Fermat's little theorem, which is the topic of today's lesson, he unfortunately would lose his eyesight in his remaining eye. And for the remainder of his life, he was blind in both eyes, but that did not deter him from continuing to publish new innovative results in mathematics. And so some of the results that we're going to cover later on were actually published in the part of Euler's life where he was completely blind. He was fortunate to have assistants who would transcribe what he told them, and that's how he would publish for the remaining 17 years of his life. And so that's just something just to keep in mind with Euler, because oftentimes we talk about his work, his theorems, but the circumstances in which he lived and the fact that he was able to accomplish so much is just phenomenal. And so today, the shortcut that we're taking to Euler's theorem is things that took Euler time to realize and develop and see that that was the right way of phrasing them. We also have to be mindful that we're doing all of this in the language of modular arithmetic, which Euler did not have. And so our results, while they are morally the arguments that Euler used, are much simplified by having reliance on the congruence classes of modulo n. So I'm going to go ahead and just put this out there. So this is the story that I just mentioned with the product and the infinite expansion today is known as Euler's pentagonal number theorem, which he showed in 1750. If you're curious in terms of like when these things actually are valid and converge, then you do have convergence if Q is a complex number whose modulus, which is the complex number analog of absolute value, is less than 1. So this is just the distance in the complex plane to the origin of a point Q. And so this is the statement that Euler would prove in 1750, which Bernoulli responded that he was just unwilling to even attempt. But no, Euler has done a lot. And so today we're going to go through and see one of his interesting results and deductions based on trying to generalize Fermat's-Little theorem. So we saw last time this function phi of n, and so let's go ahead and define it precisely. So we're going to define phi of n for a natural number n to be the number of integers a which satisfy the inequality 0 is less than or equal to a, which is less than n, and the GCD of a and n is equal to 1. So a is relatively prime to n. We can write this in another way. We can say that this is the set of integers a satisfying the inequality. And so this is just what we just said. And then now the brackets here mean the number of elements in the set, or in other words, in the language of math structures, the cardinality of the set. But if we replace all of this in the language of modular arithmetic, we can just say that this is the set of the elements, the congruence classes of a in the integers modulo n, such that a bar is a reduced residue. For homework, one of the results that you will prove is that if p is a prime number, then phi of p is equal to p minus 1. So now what we want to prove is the following lemma. If p and q are distinct prime numbers, we want to show that the Euler phi function is multiplicative. That means if phi of p times q, if we take phi of p times q, that is equal to phi of p times phi of q. So how do we prove this? So the proof is going to have us consider 3 different sets. And so one of those sets is going to correspond to, the cardinality of that set is going to correspond to phi of p times q. So we're going to go ahead and consider the following. So we're going to let t1 be those integers a such that 0 is less than or equal to a, less than p times q, and then the GCD of a and p times q is 1. So we're looking at those integers satisfying this inequality that are relatively prime to p times q. And then t2 is just going to be the negation of this. So we're going to be looking at, well, just to be precise, not the negation, but the elements that are not relatively prime. And so not relatively prime. And so we have these here. And then our next set is going to be the whole set. So those integers where we're not making any conditions on them being relatively prime. So we have this here. So what we can see, so we see here that S is equal to T1 union T2, and the order of T1, by definition, is phi of P times Q. So we have this here. But we also know that the order of S, so I'm going to put a comma here, and the order of S is equal to P times Q. And so we have these cardinalities for each of these three sets. Now, what if we look at S minus T1? So moreover, so now let's look at S minus T2, and then by construction this is going to be equal to T1, and so consequently we have that the cardinality of S, which is P times Q, minus the cardinality of T2 is equal to phi of P times Q, which is we have the cardinality of T1. So what we are going to do for this proof is deduce the multiplicative property of phi of P times Q by finding a formula that tells us what is the difference, what is the order of T sub 2, and that will allow us to deduce this here. So I've gone ahead and just rearranged things to give myself more space to write here. So we're going to go ahead as a recap. We're going to prove this by solving for the order of T2, the cardinality of T2. So the way we're going to go about this is by choosing A in the set T sub 2. How do these elements look like? Well, if A is in T sub 2, that means that A is not relatively prime to P times Q. So then, the GCD of A and P times Q is not equal to 1. So in particular, but P and Q are distinct primes, and so therefore, P or Q divide A. So let us suppose that P divides A. So we know that A satisfies the inequality that A is between 0 and P times Q. So if P divides A, this means that A occurs in the following list. So we're going to be looking at those multiples of P in that interval. So of course we have P. We're going to have 2P, and then 3P, and we're going to continue in this way until we get to Q minus 1 times P. All these are possibilities, but we also have that 0 is included, so technically we do have a 0, so we do have P divides 0. And so we have this here, so that's our this. If instead we go ahead and do the same argument but with Q, so similarly, if Q divides A, then A is in the list where now it's just everything but with Q. We have 0Q, then 2Q, 3Q, and then we just continued counting through all the multiples until we get to P minus 1 times Q. And so this is going to be, but that's it. Because we know that P or Q divides A, we have now deduced all the possibilities for what A could be. Moreover, we also see that if we look at the intersection of these sets, if we look at the intersection of the first set that we have, so 0p, 2p, all the way to q minus 1 times p, and then intersect it with 0, comma q, 2q, all the way to p minus 1 times q, the only element that they have in common is 0, because p and q are distinct primes. And we're counting down all the way until we get to q minus 1, and similarly to p minus 1. So all these numbers, so here 1, 2, 3, that we're multiplying to q, are not divisible by p. And then that holds true over here. And so we have this. But now that tells us, because the union of these two sets is going to be equal to t sub 2, so we have the same set here, union this is t sub 2. So we can use this information to count how many elements are in T2. So specifically, T2 is equal to the number of elements here, but this set has Q elements, and this set here has P elements. So we have P plus Q, but then we have to keep in mind that P elements in here, Q elements in here, but both of them have a 0 in common, so we're double counting Q twice, so we want to make sure we subtract that off. So we have P plus Q minus 1. But now, we come back to what we said earlier, that the set that we want phi of PQ, that cardinality is T1, which is PQ minus the cardinality of T sub 2. So putting everything together, so lastly, we get phi of P times Q is equal to P times Q minus the cardinality of T sub 2, which we have now established. So we have P times Q minus P minus Q plus 1. So we have this here. But now this here is going to be equal to P minus 1 times Q minus 1. So we multiply this out, we can see that's PQ minus P minus Q plus 1. And so we have our formula for phi of P times Q. But if we now take into account the lemma that you'll be proving for homework, for a prime P, the Euler phi function at P is P minus 1. And so this is phi of P, so it's phi of Q, and that concludes it for this proof. So now we're going to generalize the argument that we just gave. Our argument relied on the fact that we had two distinct prime numbers. Now we're going to be doing it for any relatively prime natural numbers, m and n, specifically showing that phi of m times n is equal to phi of m times phi of n. We know from our section on the Chinese remainder theorem that we have this bijection of the congruence classes of the integers modulo m times n with the integers modulo m Cartesian product integers modulo n. And so that's going to be our key result for proving this. So here's how the proof goes. So we're going to consider three sets. So we're going to consider the set A1. And so this is going to be the set of congruence classes in the integers modulo mn, oops, that was supposed to be an n, such that S bar is a reduced residue. Then we're going to consider A2, and that's going to be the collection of congruence classes, but now in the integers modulo m, such that A bar is a reduced residue. So I'm going to go ahead and abbreviate this time around. So this is reduced residue. And A3, same definition, but now with the integers modulo n. So we have this. So notice that we have the following. So in particular, actually by definition, we have that the cardinality of A1 is just phi of mn. The cardinality of A2 is phi of m. And the cardinality of A3 is phi of n. Because we define the Euler phi function to be those numbers relatively prime to the element we're modding out by. But the number of elements but that's just counting the reduced residues modulo mn, m, and n respectively. So we do have these here. So it suffices to show that that A1 is equal to the product of the cardinality of A2 with the cardinality of A3. Here's how we use the Chinese remainder theorem. We know that f is a bijective function, so let f be as defined in proposition 196. Then f of A1 is a subset of A2, of the integers modulo m, Cartesian product integers modulo n. Since f is bijective, we have that the cardinality of f of A1 is the same as the cardinality of A1, because f is a injective function, so we know that the image of f of A1 is in cardinality the same as the cardinality of A1. So we have this. So actually we claim that f of A1 is equal to the Cartesian product of A2 with A3. And so in other words, the image of A1 is equal to the Cartesian product of A2 with A3. So how do we show this? So for the claim, let's go ahead. So let S bar be an A1. Then f of S bar is equal to S bar, comma S bar. But I'm going to use the notation that we introduced when we were proving this in the Chinese remainder theorem, so that we can establish which congruence class we are working with respect to. So here is mod mn, and this is equal to S bar mod m, and then S bar mod n. So we have this here. Now, because S bar is relatively prime to m times n, we have that S bar is relatively prime to, that S bar is going to be relatively prime to m and n. So I'm going to write this down. So by assumption, we have that the GCD of the integer s that we're looking at the congruence class with mn is equal to 1, and thus the GCD of s with m is equal to the GCD of S with N, which is equal to 1, which shows us these are residue classes. These are reduced residues because they're relatively prime. And so we got that f of S bar mod Mn is in the Cartesian product of the reduced residues. And so this is A2 Cartesian product with A3. So we get this. Because now we have that this here is a reduced residue and it's sitting inside, then it must sit inside A2, the set of residue classes, reduced residues of the integers modulo M, and A3, the reduced residues of the integers modulo N. So we have this containment. So now we need to show the reverse containment. So conversely, let's go ahead and now choose an element in the Cartesian product. So we're going to take x bar mod M and y bar mod N to be in the Cartesian product of A2 cross A3. But now this is an element of the integers modulo M and N. So now keep in mind we have that this is a subset of here. Since f is bijective, so more specifically because f is surjective, there exists an a bar in the integers modulo M times N such that f of a bar mod Mn is equal to f of, to x bar mod M, comma, y bar mod N. But by definition of f, this also has to be the same as a bar mod M, comma, a bar mod N. And thus, we have that a bar. So when we're looking at the congruence class modulo M, that this is the same as x bar. And y bar is equal to, so the a bar is equal to y bar mod N. So I need some more space. But now, if we look at the way that we chose x bar and y bar, these are reduced residues in the integers modulo M and the integers modulo N respectively. So by assumption, we have that x bar and y bar are relatively prime to M and N respectively. And x is equal to 1, and therefore the GCD of A and M is equal to 1. And similarly, the GCD of N with A is equal to 1, and the GCD as a consequence of N with Y. So I wrote this backwards. So it should have been the GCD of N and Y is equal to 1, because that's a reduced residue, and therefore because A and Y are congruent modulo N, then we have that this here is also equal to 1. And so with this information, we have that A bar, the GCD of A and Mn is equal to 1, which shows that A bar is in the integers modulo Mn is a reduced residue. So we have this here. But now, what that's telling us is that if we take f of a bar, by the way we have constructed this, so let's put everything together to finish this. So f of a bar, we know that that's a reduced residue. So here I'm going to just continue using notation mod Mn. This is in the image of f of a1, but more precisely, this here we know is equal, by the way we constructed this, to x bar mod m, comma y bar mod n, which everything is in the image of a1, which is the reduced residues of the integers modulo m times n. So therefore, we have that the cardinality. So we have that f of a1, we have completed our double set inclusion. So this is equal to the Cartesian product of a2 with a3, which is what we wanted to show. But now that we have shown that, we have that the cardinality is exactly what we want. So we have this here. And so finally, we have that the cardinality of a1, which we know is the cardinality of f of a1, since f is a bijective function, is equal to the cardinality of a2 Cartesian product with a3, but neither of these is empty, so we have that this is the product of a1 that's a2 with a3, which is cardinality of m times the cardinality of n, and over here we have the cardinality of m times n. And so now we have the desired multiplicative property of the Euler phi function. And so we have now established this, which is getting us one step closer towards proving Euler's theorem. So the result we just proved is actually a consequence of more general structure that we have from proposition 1.9.6. In our proof, we only used the fact that it was a bijection. In abstract algebra, you actually prove that this is what is called a ring isomorphism. So a ring isomorphism between two rings is one that preserves the additive and multiplicative structure of the ring. So specifically, we take f of a bar plus b bar, we will get back f of a bar plus f of b bar, and if we took f of a bar times b bar, it will be f of a bar times f of b bar. So here's what we call, when we say isomorphism, this is derived from Greek. So specifically isos, which is same, and morphe, which means structure. And so structurally, both of these rings are exactly the same, and consequently, it comes with no surprise that we have that the number of reduced residues in the integers modulo m times n is exactly the same as the ones in the integers modulo m Cartesian product integers modulo n. And so this is just something just to throw out there for those of you who have not taken abstract algebra, that we can go ahead and abstract these notions. But in Euler's time, this was not the case. Actually, results like the one that we're looking at that in this generality would have to wait until Emmy Noether's work in the early 1900s, which led to the rise of ring theory. And so, for these reasons, Euler struggled in proving these results, is that that language that we are using here was not known to him. So he had to go ahead and develop this language on his own, while also not having the luxury of the integers modulo m, which is what we have used to simplify everything. So now we can go ahead and get to Euler's formula for computing phi of n. And so once Euler had this lemma, he was able to then prove the general formula for how phi of n looks like, because we know we can use the fundamental theorem of arithmetic and the previous lemma to show the left-hand side. So for homework, I will have you prove this equality. And so that will be part of your homework assignment. I'm going to focus in my proof on focusing this equality over here. So one thing I want to note is that most books usually use this notation for defining what phi of n looks like. But we actually have these two different products that can give it to us. So the way that we go from here to show this equality is in the following way. So over here I am assuming that the natural number n has the prime factorization pj to the aj, where each prime pj is a distinct prime. And so we go ahead and write down the product from j equals to 1 to k of p to the j minus 1. But actually, I'm not going to skip a step, so I'm going to go right in like this. I'm going to go ahead and expand that out. So you're going to have p to the j to the aj minus p to the j to the aj minus 1. So when we do that, now I'm going to factor out in those parentheses a p to the j, aj, and that leaves us a 1 minus 1 over pj. But now that's the same as writing this as two products. But now the left-hand side is going to be n. That's just because by definition of how we define n to be. And then we have now the right-hand side, that this is 1 over p sub j. And so we're done. And so for homework, you'll show this equality here, but that is a matter of applying the fundamental theorem of arithmetic, which we have here, and then we use the lemma, which tells us if we have relatively prime numbers, then phi of m times n is equal to phi of m times phi of n. And so what you want to do there is let m be pj to the aj for some j, and then similarly n will be similar the next prime to its power, and then apply that formula iteratively, and you'll prove this theorem. So now we have come to the grand finale. We're ready to prove Euler's theorem. And we have done all the hard work already. And so I've gone ahead and included a couple of results we're going to be using, specifically what it means to reduce residue, and this corollary of that we have the natural numbers n, a bar is a reduced residue, and we have the list of all the reduced residues m1 through mk. Then multiplying out still gives us back the same number of reduced residues. So with that in mind, let's go ahead and do this. So let's prove the theorem. So we're going to go ahead and consider let m1 bar, m2 bar to mk bar be the distinct reduced residues of the integers modulo n. So in particular, because there are k reduced residues, we have that k is equal to phi of n by definition. So we have k is equal to phi of n. Now by the corollary that we have above, so this is the 1.11.3 or 924 in the book, we have that a bar times m1 times a bar times m2 all the way to a bar times mk is the same as taking the product of m1 times m2 bar all the way to mk bar. But now, this tells us that a bar is appearing on the left-hand side k times. 1, 2, all the way to k. So we have k. So we have a bar to the kth power, which is phi of n, times m1 bar times m2 bar all the way to mk bar, which is equal to m1 bar, m2 bar, all the way to mk bar. But this here is the whole product is a reduced residue. So we have a multiplicative inverse for both of these. So we go ahead, so let n bar, so multiply by the multiplicative inverse of m1 bar times m2 bar all the way to mk bar, then gives us that a of phi of n times multiplying the multiplicative inverse of all of this will give us a 1 and a 1 on both sides. Or we can just cancel. We're just canceling out here. So we have that this is equal to 1 bar. And now we have proven the result. And we have now accomplished what took Euler 27 years to prove in the span of under an hour. But the main thing I want to emphasize is we have the luxury of these tools that Euler did not have. We were able to use the integers modulo n, their properties. We used the Chinese remainder theorem, but specifically that extension of having a bijection between the integers modulo m times n and the integers modulo m times n, because that's really the hard part of this proof. This here was not so bad. The difficulty was this lemma. And that's what really caught Euler off guard, is how do we establish this statement is true while not having the benefit of being able to use this bijection that we employed. But with these assumptions in mind, as we have seen, the proof is not so bad. And so that's just something that is just we benefit from all the work that has been done in the time since Euler. So some of the questions in the homework assignment will have you apply Euler's theorem from a computational point of view. So we have, just to mention here, we do have a restatement of Euler's theorem. If we translate from congruence classes to mod n notation, we have that a to the phi of n is congruent to 1 mod n whenever a and n are relatively prime. So the next thing we want to do is compute what is 217 to the 73rd power modulo 108. So whenever you're doing these computational questions, the first thing we want to do is compute phi of 108. But now, when doing this, we want to break it down into its prime factors. And so we have that 108 is 4, so 2 squared, times 27, so 3 cubed. So we know that by the multiplicative properties that this is going to be phi of 2 squared times phi of 3 cubed. If we apply the formula for computing the Euler phi function at primes, and specifically for just any natural number n, and then 2 squared and then 3 cubed, what you're going to get there is that this will be 2 minus 1 times 2 to the 2 minus 1, and then that will give us the phi of 4. And then the next one will be 3 minus 1 times 3 to the 3 minus 1. So we'll have this here. So this is going to be 2 times 2 times 3 squared, so 9. And so we have that this is going to be 4 times 9. So we're going to have 36. So we have that we're looking at phi of n is equal to 36. The next thing we want to do is look at the exponent and reduce this, specifically apply the division theorem modulo with respect to 36. So that's going to be also this akin to taking the remainder. So when we look at 73, we can see that this is 73 is equal to 36 times 2 plus 1. So now we can go and apply Euler's theorem. So we have 217 to the 73rd power, which is 217 to the 36 times 2, which I'm going to write like this, times 217 to the 1. Since 217 is relatively prime to 108, we get that by Euler's theorem that this is going to be 1 mod 108 times 217 to the 1, which is 217 mod 108. So we have this. But now 217, if we multiply 108 times 2, that's going to give us 216. So we have that this is congruent to 1 mod 108. And so we have gone ahead and computed this. Now, this is one of the questions in the book, specifically exercise 935, but we could actually do this without applying Euler's theorem. So we just gone ahead and applied Euler's theorem, but what if we had done this instead? So 217 is congruent, as we just saw, to 1 mod 108. So that means that if we're taking 217 to the 73rd power, that this is the same as taking 1 to the 73rd power mod 108. And so that's just 1. So while Euler's theorem works for this one, we can actually bypass Euler's theorem by just computing it directly in this way. So that concludes it for this lesson. So we have proven Euler's theorem. So now we're going to be moving onwards. So the next lesson will be proving what is known as Lagrange's theorem. But for those of you who have taken abstract algebra, we will be seeing the first instance of Lagrange's theorem, which would eventually over time become the result that is proven in abstract algebra. But the statement that we will be proving in the next lesson, what it says is that if we have a polynomial, f of x, and the degree of this polynomial is equal to n, then f of x has at most n roots. So we're going to be considering f of x will be a polynomial over, say, the real numbers, rational numbers, but also over the integers modulo p. So we're going to be doing this in more generality. And so this is what is known as Lagrange's theorem. And that will be the context for the next lesson.